Hello everyone, my name is Qinjin. I'm from Renmin University of China. I'm glad to present some of our works related to language and vision for video understanding. I will mainly focus on image and video captioning in this talk. Let me first briefly introduce what we do in our lab. So the idea or motivation behind our work is that we humans live in a multimodal world. We learn, we think, and we express through multiple modalities. Therefore, for AI systems, they need to have the ability to understand the multimodal world. Our work focuses on building systems that can understand from multi-level, multi-aspect, and multimodal. For example, understanding the video content can be from low level to high level. As shown in this example video, we can clearly see there are dogs, a man, and a man wearing a dog t-shirt. Such objects and attributes can be considered as low-level understanding, while the relationship between the object and object can be considered as mid-level. And understanding the overall event happening in the video and describing it using natural language sentences can be considered as a higher level understanding, which will be the topic I will discuss today, captioning of the semantic content. The image or video captioning task is that given an image or video, the system can understand the semantic content and express it using natural language sentences. The agenda of my following talk is that I will first present our recent work on controllable image captioning, and then I will present some works related to short video captioning, which generates single sentence description for short videos, and dense video captioning, which generates dense captions for multiple events in the video. Most current image captioning models can generate fluent and visually relevant sentence descriptions for an image. However, most models do not consider the user intention and only passively generate image descriptions. Therefore, such models fail to realize different user intentions and tend to generate most frequent and safe mediocre descriptions. To address such limitations, there have been a few works proposed to actively control what to describe. For example, a single object or a set of objects. However, none of these models can control caption generation at a more fine-grained level. For example, how many attributes should we describe for an object? Or should we describe the relationships with other objects, or what is the description order, and etc. In our recent work, we proposed the abstract scene graph ASG as the more fine-grained control signal. The ASG is a directed graph containing three types of abstract nodes: the object, attribute, and relationship. The abstract nodes are grounded in the image but do not need to contain any semantic labels. Therefore, such a graph structure can reflect user's intention, fine-grained intention. For example, what to describe, how detailed, and the order of description. Since the nodes do not need to contain semantic labels, it is easy to construct the ASG automatically or designed by users. We then propose an ASG to caption model to generate image captions based on the ASG control signal. Given an image and an ASG, we first use a role-aware graph encoder to obtain graph representations. It contains role-aware embedding module to differentiate the fine-grained intentions of abstract nodes, and a multi-relational graph convolution network to improve semantic representations with the graph context. Then the encoded graph is fed into the language decoder specifically designed for graphs. Firstly, the ASG not only controls what contents to describe, but also implicitly decide the order of description via graph structures. We propose a graph-based attention mechanism to consider both graph content and graph structures. Secondly, it is important to fully cover information in ASG without omission or repetition. Therefore, we propose a graph updating mechanism to gradually update the graph representation during decoding. Here, we show the experiment results of our model comparing with carefully designed non-controllable and controllable baselines on both visual genome and MS-COCO datasets. Due to the use of control signals, controllable approaches outperform non-controllable methods. And our ASG2 caption model also achieves very large improvement over controllable baselines in both semantic quality and structure alignment performance. For the diversity of generated captions, we compare our model with the diversity-driven approaches. We can also see that our model can generate more diverse captions due to the diversity of sampled ASGs. Here we show some visualization examples. For example, the ASG1 contains more attribute nodes than ASG0. That leads to the generated caption from ASG1 contains more details, for example, the women hair color, than the sentence from ASG0. And also in this example, the ASG4 has edges of inverse direction that comparing to ASG3, which leads to the generated captions has the opposite description order. These examples demonstrate that the generated caption can faithfully follow the ASG structure, and also the diverse ASGs can lead to diverse image captions. So for more details of our work, please refer to our paper and then check out the codes and datasets. Next, I will present some works in video captioning. So depending on the video duration, we normally can categorize captioning into short video captioning or long video captioning. So for short video captioning, basically we deal with videos in 5 seconds to 20 seconds long with a single event. So basically we aim at generating one sentence to describe the event. While for longer videos, we normally deal with untrimmed videos, typically 5 to 10 minutes long with multiple events. And then therefore we need to detect meaningful events in the video automatically and then generate multiple sentences to describe the different events. Next, I will present some works for short video captioning. Short video captioning, also called video to text, is one of the core evaluation tasks in the NIST track rate evaluation, which aims to describe the video content with a natural language sentence. We can generally divide different solutions for video to text into two categories. One is based on retrieval, which selects the sentence from an available corpus through a video to text matching. And the other type is a generation type approach, which basically generates sentences via the captioning model. So the following approaches are also verified in our effort in the track rate video to text evaluations. We are the winners for 3 years from 2017 to 2019. First, I will present our solutions for the video text matching. This figure shows the overall framework of our baseline video to text matching model. So it basically contains 3 main components: video encoder, text encoder, and joint embedding. For the video encoding, we basically combine 3 levels of encoding, including the level 1, which is the main pooling of frame level encoding. Level 2 applies bidirectional GRU over the frame CN encodings, which aims to encode the temporal information. And then level 3 applies convolutional neural network over the hidden state sequence in order to encode the local information. For the text encoding, we also combine 3 levels of text encoding, including the level 1 mean pooling over the word encoding. Level 2 applies bidirectional GRU over the word sequence. And the level 3 applies convolutional neural network over the hidden state sequence in order to encode local information. With the independent encoding from the video and the text sides, we embed them into the same space and train a joint embedding through the ranking loss. The above baseline video text matching model tries to do the cross-modality matching at 3 levels. However, it still does not explicitly consider the fine-grained semantics in either modality. In order to realize more precise matching of video and text, it is important to understand the fine-grained semantics in the matching sentence. The sentence naturally contains hierarchical sentence structures. The overall sentence describes the event, and the event normally contains different actions, and the action relates to different entities. For example, the noun phrase "an egg is the patient of the action broken." Such structure can help understand the fine-grained local components in the sentence and how the different components compose the overall event. In this work, we propose to take advantage of the hierarchical structure of the sentence and match the video and the sentence at global and local levels. Our proposed hierarchical graph reasoning model contains 3 main components: the hierarchical textual encoding, hierarchical video encoding, and multi-level video text matching. The hierarchical textual encoding is the main component. We first decompose the sentence into a semantic row graph. The red node is the event node. The green nodes are the action nodes, and the yellow nodes are the entity nodes. We then initialize the graph nodes. We first use LSTM to obtain contextual word embeddings. The event node is the weighted average of word embeddings to focus on more salient actions. And the action and entity nodes are the max pooling of their constitutive words. In order to capture the interactive context of different nodes, we use attentive relational graph convolution network to encode the graph. We factorize the relation matrix in order to avoid overfitting. Finally, we get the textual encoding at 3 levels corresponding to event, action, and entity. Well, videos also contain multiple aspects, such as objects, actions, and events. However, it is challenging to directly parse the videos as similar as texts, which requires object detection, object tracking, action segmentation, etc. We therefore encode the video into corresponding 3 levels by a symbol approach. We use different weights for each level, which are decided by different level of text, so that we can focus on different aspects in the video. We then match the video and the sentence at all 3 levels. At the event level, we use the cosine similarity for the global matching. At the action and entity level, we use attentive alignment in local matching. The model is trained using contrastive ranking loss. For the in-domain cross-model retrieval, our HGR model achieves consistent improvements on 3 datasets. For the cross-dataset video text retrieval experiments, we train models on MSRVDT dataset and test on YouTube to text. Previous approaches suffer from performance loss from in-domain retrieval to cross-dataset retrieval. But our HGR model achieves consistent improvement in domain and across datasets, which proves the better generalization performance of our model. To know more details about this work, please refer to our paper and check out the codes. Next, I will describe our work in video description generation, which also refers to the captioning model. In this task, we mainly focus on two challenges: comprehensive video semantic representation, which can provide support for comprehensively describing the video content, and a caption generation, which can generate accurate and fluent descriptions for the video. Next, I will mainly describe our three solution strategies in our system, which are multimodal fusion and semantic concept enhanced video description generation, and a topic-guided video caption generation, re-ranking with self-defined fluency and relevancy rewards. For video semantic encoding, because videos inherently contain multiple modalities to deliver rich semantic information, comprehensive understanding of the video needs to combine the multiple modality information, such as 2D visual features and 3D visual features and audio features and etc. We also employ concept to reduce the representation gap between video and text. We can take advantage of pre-trained concept detection using TGIF and then previous track data for about 15,000 concepts. And based on the video semantic encoding, we build a caption generation module. We consider the type of the video or topic of the video is one of the important factors that can affect the caption, because we consider the vocabulary varies under different topics and the language style varies under different topics. We therefore propose a video caption generation model with latent topic guidance. So the caption generation is formulated as a conditional sentence probability, and we factorize it over latent topics. And then we parameterize the latent topic distribution and topic-aware sentence distribution, which corresponds to the topic predictor network and topic-aware caption generation network. And we integrate the topic prediction and caption generation into the multitask framework. Basically, we use existing topic mining approaches to generate a set of latent topics as teacher topic, and then use the teacher topic to guide the latent topic learning by an additional topic loss function. In the caption generation module, we also integrate the temporal and semantic attention and apply the reinforcement training strategy, and the reward functions are self-supervised fluency and visual relevancy rewards. Specifically for fluency reward, we use the language pre-trained on ground truth captions. These fluent captions will have higher complexity measured by this language model. So we use the average log probability of each word generation as the fluency reward. For relevancy reward, we pre-train the visual text matching module so that semantically similar videos will have closer feature vectors in the joint space, so we can use the constant distance between video and text features as a relevancy reward. After training different caption models with different features and strategies, we propose a re-ranking strategy to ensemble different models. Specifically, we apply multi-aspect re-ranking considering the relevancy and the fluency. The relevancy and the fluency measurement are as described above, and it can help us to select candidate captions from different models. This figure shows the side performance of the track weight video-to-text evaluation in 2019. The 4 runs from our system all significantly outperforms other participating systems. Finally, I will present our efforts in dense video captioning. As shown in the figure, the dense video captioning task aims to describe an untrimmed video with multiple sentences. It needs to detect meaningful events in the long video and generate descriptions for each event. Therefore, the event detection is very important to the informative caption generation. Dense captioning of events in videos is one of the core challenge tasks in the ActivityNet large-scale activity recognition challenge. So we participated in this evaluation for 3 years, starting from 2017, and then this year is our third time that we won this evaluation. Next, I will present our solution, our system for this challenge. As mentioned, event detection is one of the vital parts in this dense video captioning task. So the typical events detection methods usually follow a two-stage approach, so which includes a candidate proposal generation stage and a proposal selection stage. In the proposal stage, a large amount of event candidates are proposed by sliding window or neural networks such as SST. Then the event classifier are designed to predict event confidence for each candidate. And the proposals with the confidence higher than a fixed threshold will be selected at the final event proposal. So the limitations or drawbacks of the two-stage approach include, first, it needs to generate enough candidates to ensure covering all the possible events. The amount of proposals usually about 1,000, and hence it is not efficient and computationally expensive. The second problem is that the temporal relationship between the events are not considered in such an approach. As a result, it may lead to selecting events with high redundancy. Based on our analysis, we find that the descriptive events in a video are highly temporal related. They usually follow some temporal orders as shown in the figure. There are mainly 3 types of event temporal orders in the ActivityNet dataset. The first is the sequential order, where the events are one after another, maybe with only small overlap. Based on our statistics, there are about 82% videos contain sequential events. The second type is the summary to details type of order, which first summarizes the general event, such as a woman is making juice with the food, and then describes some detailed events, such as showing the fruit, putting the fruit into the juicer, and drinking the juice. Such type covers about 17% of videos in the dataset. Only small portion of videos follow the detailed to summary sequential order. This type order only covers about less than 1%. Overall, we can see that about more than 98% of videos have explicit temporal orders. Therefore, we can exploit the temporal relationships between the events to generate event proposals. The events detection can be solved as a sequence generation task based on only one pass generation. This is the overview of our proposed event sequence generation module. I will explain in details for each part. We first encode the video and model the context information. We divide the video into several segments and extract the segment-level video features from 3 modalities. Based on these segment-level features, we further capture the context information with a bidirectional GRU. The hidden states of 2 directions are then concatenated and added to the segment-level feature. With these context-aware features, we can generate the event sequence step by step. We first represent each event with a t-dimensional binary vector, EI. Each value of the vector xi denotes if the corresponding segment is included in the event. We denote the special start event and the end event with the all zero vector. We use a GRU as the event decoder and initialize it with global video feature. At each decoding step, we feed the previous event to the decoder and predict the current event distribution over the whole video timeline. The period where predicted probabilities over 0.5 forms the generated event. In such way, we can generate the event one by one until the special event and event is generated. For forward pass, we generate the event sequence only depending on previous event information. The future events are also helpful for the current event prediction. Therefore, we train another event generator with the whole video reversed and generate the event sequence with future event context. Finally, we match the corresponding events in two directions and average their distribution maps to get the final event boundaries. We use the binary cross-entropy for the model training. For faster learning, we utilize the teacher forcing training strategy by feeding the ground truth event at each decoding step. We compare our proposed event detection module with other two-stage methods, such as ESGN, proposed in 2019 CVPR. Our full module with bidirectional temporal dependencies outperforms the baseline in both average recall and precision, and the improvement is especially obvious on the high TIOU. We can also see combining the predicted distribution from two directions outperforms the single direction, which shows both the past and future events are helpful for the current event detection. We also calculate the basic characteristics of generated proposals. There are on average 2.89 events generated for each video. The average length is also close to the ground truth with about 41 seconds. And more importantly, the self-TIOU of generated proposals is only 0.07, which demonstrates the proposed model can generate events with much less redundancy. And this is self-visualization example. We can see the proposed event sequence generation module can generate more diverse and accurate events without redundancy, while the two-stage module will select similar high confidence proposals without considering the temporal relationship between the events. For the captioning model, we use an intra-event captioning model with local context, global context, and event location information. For the decoder, we use a two-layer stacked GRU. More details can be found in our report in this year's challenge and last year's challenge. We also apply event proposal re-ranking and caption re-ranking to further improve the results. We train the captioning model with cross-entropy loss and fine-tune it with self-critical reinforcement learning algorithm. Training with meter reward makes improvement on the meter metric for both ground truth proposals and generated proposals. And also the re-ranking, caption re-ranking is also beneficial to achieve better performance. This is our final submission for the challenge. It is still a very hard task. To summarize, in today's talk, I presented some works concerning image captioning and video captioning. For image captioning, we propose a controllable image caption generation model with abstract scene graph as a control signal, which considers user intention and improve diversity. For video captioning, I presented some works for short video captioning, retrieval-based with the fine-grained video text matching model, and generation-based with topic guidance and self-supervised rewards, and etc. And for dense video captioning, we propose to consider the sequential temporal event information and to generate event sequence in one pass, and which also is a winning solution in ActivityNet dense video captioning. So thank you very much for your listening, and then if you have any questions, please feel free to contact us. Thank you.